Hi, Assalamualaikum warahmatullahi wabarakatuh, and a very good morning, everyone. So, today we are going to continue with Chapter 6 Chemical Equilibrium, Subtopic 6.2 Equilibrium Constants, Part 2. Okay, so last time we have covered Equilibrium Constants, Part 1, where we have learned about equilibrium types of equilibrium reaction, which are homogeneous and heterogeneous, and we have learned about equilibrium constants Kc and Kp and the relationship between them. So today we are going to cover the following outcomes, which are: first, we are going to calculate Kc, Kp, or the quantities of specific uh, or the quantities of species present at equilibrium. And then we are going to determine the degree of dissociation alpha, and then we're going to predict the direction of net reaction by comparing the values of Q and K. Alright, so without further ado, let's get started. Alright, Bismillahirrahmanirrahim. Okay, so in the chemical equilibrium questions, there are usually two types of equilibrium problems. Okay, the first one is, the first one is where it gives the equilibrium quantities such as concentration and partial pressure for us to solve for the Kc and Kp. For example, just like what we did in 6.2 part 1, the previous video, where the question gives you the equilibrium quantities such as the concentration and the partial pressure in at equilibrium, and it asks you to find the value of Kc and Kp. So that one is kind of a simple question, straight to the point. Okay, however, the second types of problem is when it gives you the initial quantities. For example, it gives you the quantities of initial concentration and initial partial pressure before the system achieve the equilibrium state, and it gives you the value of Kc and Kp for us to solve, to find the equilibrium quantities, to find the concentration and the partial pressure at equilibrium state. So this is what we want to learn in this 6.2 part 2, where we are going to learn a new method to solve for this kind of problems. Okay, so now, the methods that we are going to use here is named ICE table method. So a table called ICE initial change equilibrium table is used to determine the equilibrium concentration or partial pressure of each reacting species. Okay, so this ice table is usually for us to find the concentration and partial pressure at equilibrium state, where the question usually gives you the initial concentration or partial pressure as well as Kc and Kp for you to find this using the ice table method. So this is how the tables will look like. They have the species name, and then we use the initial change and equilibrium, where you find this ICE, ICE table. Okay, so the unit for this can be in molar, mole per dm cube, or mole, or atm. So atm for pressure, this is for concentration, this is this is like rare question lah. Sometimes maybe that they want you to find the amount of the reactant or product in terms of mole, so then you can use this. Okay, I remember that you need to always use ice table when solving equilibrium process, actually, because it kind of like really convenient for you to use ice table. Okay, especially when it doesn't give you any of the equilibrium concentration and partial pressure. Okay, so now we are going to try solve problems using ice table. So the first example that I'm going to show you is example on calculating equilibrium concentration. Okay, so for now, let's read the question. It says that the equilibrium constant Kc for the decomposition of dinitrogen tetroxide N2O4 gas to nitrogen dioxide gas is 4.6 times 10 to the power of negative 4.6 times 10 to the power of negative 3 at 25 degrees Celsius. Calculate the concentration of all reacting species at equilibrium if 0.1 mole of N2O4 is introduced. So this is introduced is the keyword for initial, okay? In a 5 decimeter cube flask at 25 degrees Celsius. So what is the first thing that you need to do? The first thing is for you to do is you do the chemical equation. So balanced chemical equation. So it says that here the dinitrogen tetroxide gas is decomposed into nitrogen dioxide gas. So N2O4 gas decomposed into 2 mole of nitrogen dioxide gas. So you do the chemical equation, then you do the ice table like this. So the ice table must consist of initial change and equilibrium in unit molar, mole per decimeter cube, or M, or the capital letter M. Okay, and then do this kind of table. And then the second step you need to do is extract out all the information from the passage into at the side of the table, beside the table, so that you can see it clearly. So for example, Kc is 4.6 times 10 to the power of negative 3. And then temperature is at 25 degrees Celsius, both equilibrium and initial. And then the volume of the flask is 5 decimeter cube, and the mole of N2O4 is 0.1. So this is the initial N2O4, because it says that 0.1 mole of N2O4 is introduced in a 5 decimeter cube flask at 25 degrees Celsius. So what's the point here, guys? So the point is you can find the molarity of N2O4, the initial molarity of N2O4. So you can find here, you can find the value here. So you know that. So first step is step 1. So first thing is you need to find the molarity. So you know that concentration is equals to number of mole over volume. So you can find that the initial concentration of N2O4 is equals to 0.10 mole divided by 5.0 decimeter cube, where we can find that the molarity of N2O4 gas is 0.02 molar. So this is the initial concentration of N2O4 gas, dinitrogen tetroxide gas. So what you need to do is you can fill in the table here. So this is the initial molarity of N2O4 gas. So initial is 0.02 molar, where this one is before the reaction happened. Okay, so before the reaction happened, what is the initial concentration of nitrogen dioxide? There is no, right? No, because the nitrogen dioxide has not yet been produced or formed. So this one is 0. Okay, now change. So what are you going to put here? Here you are going to put the unknown, where you want to put X. Okay, Okay, however, okay, for this one, you need to know whether the sign is negative or positive. So, if the concentration of the species is decreases throughout the reaction, then the sign is the negative. So here, the N2O4 gas is going to be decomposed into nitrogen dioxide gas. So it means that the concentration of N2O4 will be decreasing over time. So it will have the negative sign. And why it's X here? Because it has the coefficient stoichiometric of 1 here, so the negative X. Okay, however, throughout the reaction, the concentration of nitrogen dioxide will be increasing because it will be formed throughout the reaction. So, it will have a positive sign here. Okay, so now since the coefficient she has is 2, so it will be 2x. Okay, so this is negative because it will be used to form this. So this is reducing, this is increasing. So this is x because it has one it has 1 as a stoichiometric coefficient. This one is 2 because it has 2 as a stoichiometric coefficient. So negative x plus 2x. So at equilibrium, so for equilibrium is initial minus change. So initial here is 0.02 minus x, and for the equilibrium here is initial minus change. Oh, ni tak ada lah, tak ada apa. So this is just 2x. Okay. This is only applicable for yang bahagian yang ni je, yang reactant, because it has been used. Okay. Initial plus change. So 0.02 plus negative x. So that's why it's 0.02 minus x. So this one is 0 plus 2x. So that's why it's 2x. Okay. So now this is what you got for your ice table. So what you need to do is you need to find x. You need to find the concentration of the N2O4 and NO2 gas at equilibrium. So the first thing that you need to do is you need to find the x. So how do you want to find the x? So remember that just now you have the given value of Kc. So you know that Kc is equals to the concentration of nitrogen dioxide squared over N2O4. Okay. So now, as unknown, you know that at equilibrium here, this is where you need to focus. This is the concentration at the moment. So you need to substitute this unknown inside this one. Okay. So you know now is Kc is equals to, so 4.6 times 10 to the power of negative 3 is equals to NO2 2x. X squared over 0.02 minus x. Okay, so this one you have to expand the quadratic equation. So you need to expand just like you do in mathematics. So what you need to do is next, this one you times with this one, right? So 4.6 times 10 to the power of negative 3 times 0.02 minus x equals to 4x squared. Okay, now you need to expand this bracket. So this one times this one and this one times this one. So you will get, and then this one you need to change the position to the left side so that this is equal to 0, just like you do in the quadratic equation formula in mathematics. So you will get 4x squared minus plus 4.6 times 10 to the power of negative 3x minus 9.2 times 10 to the power of negative 5 equals to 0. Okay. So, when you put in the calculator this value, A, 4, B, 4.6 times 10, negative 3, C, negative 9.2 times 10, negative 5, you will get X equals to 4.26 times 10 to the power of negative 3, or X equals to negative 5.41 times 10 to the power of negative 3. And this value here is not acceptable because the value of all the reacting species should be positive. Mana ada value molarity negative? So this is not acceptable. So here you can conclude that the value of X here is 4.26 times 10 to the power of negative 3. So when you already know the value of X, now you can find the concentration of N2O4 and NO2 gas at equilibrium just by substituting the value of X inside this formula, inside this unknown punya equation. So now you can get here at equilibrium, the concentration of N2O4 is equals to 0.02 minus X. So X is equals to 4.26 times 10 negative 3, right? So 0.02 minus 4.26 times 10 to the power of negative 3. So you will get the concentration is 1.6 times 10 to the power of negative 2 molar. And for the concentration of NO2 gas, you will get equals to 2x. So you will get 2 times 4.26 times 10 to the power of negative 3 will equal to 8.5 times 10 to the power of negative 3 molar. So this is the final answer for this question. Okay? Alright? So yeah, this is quite a mathematics solving problem lah. Okay? So, boleh Alright. Okay. Next, we are going to. So I hope that you will understand this part. Okay, but no worries. We are going to do this one more time after this. Okay. So next. Okay, next. We are going to look at example 2, calculating equilibrium partial pressure of species. So this time in terms of partial pressure, tadi in terms of concentration, right? So the question here said that bromine gas react with chlorine gas at 400 degrees Celsius to form bromine monochloride BrCl gas. If the equilibrium constant Kp for the reaction is 6.9 at 400 degrees Celsius, calculate the equilibrium partial pressure of BrCl when the initial partial pressure of Br2 and Cl2 are 0.34 atm and 0.51 atm respectively. Okay, so first thing you need to do is do the chemical equation. So the chemical equation, you will get bromine gas plus Cl2 gas to form 2BrCl gas. So this is in the balanced state, balanced form. Okay, and then you put initial change and equilibrium in terms of ATM unit. Okay, second step is after you do the ice table and the chemical equation, second step is you need to extract all the information from the passage beside the ice table so that you can see it clearly. So, it says that Kp here is 6.9 at temperature 400 degrees Celsius and the initial partial pressure here is 0.34 for bromine gas and 0.51 atm for chlorine gas. So, you have extract this information, then what you need to do is just put this initial partial pressure inside this table. So here you will get the initial partial pressure for bromine gas is 0.34 atm and initial partial pressure for chlorine gas is 0.51 atm. And product will always, the initial partial pressure or concentration of product will always be 0 because the product is not formed yet. Okay, next, change. So change. So it might, for the reactant, always negative sign. For the product, always positive sign. So it's negative X because the stoichiometric coefficient is 1 here. This one also minus X. This one positive because product and the punya coefficient, stoichiometric coefficient is 2. So 2x. So for the equilibrium is initial plus change. So 0.34 plus negative x is 0.34 minus x. 0.51 plus negative x is 0.51 minus x. And 0 plus 2x is positive 2x. Tak payah positif pun tak apa, you can just put 2x. Okay, so you have done the ice table. So second step is next step, the third step I think, is you need to use the Kp ni kan to find the x. Tadi use Kc to find the x, now we use Kp to find the x. So to find the x, so we know that Kp is equals to partial pressure BrCl squared over partial pressure bromine gas times partial pressure chlorine gas. Okay. So we know that the value is 6.9 here, right? And what we need to focus is here at equilibrium. At equilibrium, you need to know the equilibrium state because we need to find the partial pressure at equilibrium. So, we substitute this value inside this formula. So, we know that Kp is equals to 6.9 equals to partial pressure of BrCl2 is 2. So, 2x squared over PBr2 is 0.34 minus x times 0.51 minus x. Okay. So, okay, this is what you got lah. And then you expand this one first. So, second step for this one is you need to expand this one first. Tadi tak payah expand because it's just a simple one kan. Satu je. Now ni dia ada 2x ni. So, you have to expand this first. So, 6.9 equals to 4x squared over, expand this, you will get 0.1734 minus 0.85x plus x squared. Then, you will times this with this. So you will get 1 kat sini lah. So you will get 1.196 minus 5.865x plus 6.9x squared equals to 4x squared. So this one put here, pindahkan ke sini to equals to 0. So you will get 2.9x squared minus 5.865x plus 1.196 equals to 0. So you will solve the x, you will get x will be equals to 0.230 or x equals to negative 1.792, where this one, it is not acceptable because the value of concentration must always be positive, and the concentration and partial pressure must always equals to positive. So this is not acceptable. So now we know that the x that we are going to use is 0.230. So now we need to find the partial pressure. So at equilibrium, okay, so the partial pressure of BR2 is equals to 0.34 minus x, where x is equals to 0.34 minus 0.230. So you will get 0.11 ATM. So for partial pressure Cl2 is equals to 0.51 minus x, where it is 0.51 minus 0.230, and you will get 0.28 ATM. For PBRCL, it is equals to 2x. So it is equals to 2 times 0.230. So it is equals to 0.46 ATM. So this is the final answer for the question. So you will get the partial pressure of BRCL at equilibrium is 0.46 ATM. Okay? Alright. It's very simple. This one is very simple sebenarnya. Tak susah pun. InsyaAllah okay je. Okay, this is mathematics. You guys suka mathematics kan? Okay. Alright. So next one is we are going to look at degree of dissociation. So we have learned about ice table. So ice table 2 will be used without this chapter lah. Okay, so now we are going to look at degree of dissociation. So what is degree of dissociation? So it is the fraction of a molecule dissociated. Dissociated tu apa? Dissociate, terungkai. Macam daripada, dia macam decompose lah, macam terurai. Okay, so the values for degree of dissociation alpha, it will be ranged from 0 to 1, where 1 indicates complete dissociation. And the formula is alpha equals to amount dissociated in terms of concentration of partial pressure, or we usually know it as X. Nanti kan takut confuse pula. X over initial concentration of partial pressure C. Okay. Alright. X over C lah. So alpha equals to X over C, where X is the amount dissociated in terms of concentration of partial pressure. C is the initial concentration of partial pressure. So alternatively, it also can be expressed in terms of percentage of dissociation, where you just have to times with 100%. So it will be ranged from 0 to 100%, where 100% indicates the complete dissociation. And dissociation is actually the reaction involves the breaking of covalent bond when a molecule is broken down into smaller molecules, ions or atoms. So dia macam decompose lah, dia macam uraikan je. So kita nak tengok the fraction of the molecule dissociated to form the product. Okay, reactant dissociated to form product. Okay, so now we look at this example here. Okay, it says that this question, 0.030 mole of pure phosgene COCl2 gas was heated at 800 degrees Celsius in a 1.5 decimeter cube flask. At equilibrium, the partial pressure of carbon dioxide gas was found to be 0.50 atm. Calculate the degree of dissociation of COCl2. So, dia nak cari degree of dissociation of COCl2, the reactant. Okay, first step, you need to do the chemical equation, balanced chemical equation. So, it has COCl2 decomposed into CO gas and Cl2 gas, carbon monoxide gas and chlorine gas. Okay, so then you put the initial change and equilibrium in terms of ATM because now we talk about partial pressure. Okay, next, we extract the information from the passage beside the table. So we got the initial COCl2 gas. It has the N equals to 0.030 mole, volume 1.5 decimeter cube, and at temperature 800 degrees Celsius or 1073 Kelvin. And at equilibrium, the partial pressure of carbon monoxide product is 0.5 atm at temperature 800 degree Celsius. So this is the initial one. So you need to find the initial value, initial pressure of COCl2 for you to find the X. Okay, now what you need to do is, the next step, you need to find the initial partial pressure of COCl2 by using the ideal gas equation. So, we use the PV equals to nRT, where the partial pressure of SO3 is equals to... Oops, salah. Macam mana Miss boleh letak SO3 kat sini? This one point. That means COCl2. COCl2. Okay. Oh my god. Okay, so now what we're going to do, find the initial partial pressure of COCl2. We know that the N here is equals to 0.030 mole. R here we use the 0.08206 because the ATM kan. And then temperature in terms of Kelvin, 1073 Kelvin. Divide by volume, 1.5 decimeter cube. Okay, so you will get the partial pressure is... The partial pressure is 1.761 atm. Okay, so you have the partial pressure here. Initial partial pressure here, isi table kat sini. initial partial pressure of COCl2 is 1.761 atm, and this one is 0, 0, haven't produced yet. And the change here is reactant always negative, so negative X, product always positive, positive X, positive X. And equilibrium is initial plus change, so 1.71, 1.761 minus X, so this is X, this is X. So we know that at equilibrium, partial pressure of CO is 0.50 atm. And we know that the unknown for partial pressure at equilibrium for CO is X. So partial pressure of CO is equals to X is equals to 0.5 atm. So we know that X is equals to 0.50 atm. So now the degree of dissociation is amount of COCl2 dissociate divided by initial partial pressure of COCl2. So amount of it dissociate is X here. Right. So divide by initial partial pressure. So you will get here 0.50 over 1.761 atm. You will get the degree of dissociation is 0.28. Okay. No unit. Sebab this one cancel each other, so no unit. Okay. So degree of dissociation has no unit. So this is 0.28 lah the answer. So this is how you find the degree of dissociation. So X over C, initial partial pressure. Okay. Yay. Okay, now we are going to move on to the next part of this chapter, which is we are going to look at reaction quotient Q. So reaction quotient Q can be also defined as the mass action expression at any stage of reaction. It can be expressed similarly as equilibrium constant K in terms of concentration QC and partial pressure QP. For example, here we have this equation. 2 sulfur dioxide gas react with oxygen gas to form 2 mole of sulfur trioxide gas. So for QC, QC is expression at any stage of reaction. It's not necessarily at equilibrium. So Q. So it is the concentration of, tapi still product over reactant. So concentration of SO3 squared over concentration of SO2 times O2. QP bersama partial pressure of SO3 divided by partial pressure of SO2 times partial pressure of oxygen gas. So this is how you find the QC and QP. Sama macam KC dengan KP. Okay, what is the difference between Q and K? Okay, the difference is reaction quotient Q, the concentration and partial pressure not necessarily at equilibrium state. It is for at any stage of reaction. This is for Q. However, for equilibrium constant K, the concentration and partial pressure is at the equilibrium state. So that's the difference. So the value of Q and K can be used to predict the direction of net reaction, either to the left or to the right. Okay, so now let's predict. So here, we are going to predict the direction of net reaction by comparing the value of Q and K. Okay, so there are 3 possible cases. So the first cases is where the Q is equals to K. So when Q is equals to K, the system is said to be at equilibrium. So this is the first case. Okay, second case, we look at the left side of the table, where Q is less than K. So when Q is less than K, it is said that the reactant is small. So when the reactant is small, the net reaction will proceed to the right. It will form more product until the equilibrium is achieved. So now the forward reaction is more favoured. Maksudnya bila product is formed for the equilibrium to achieve, the forward reaction is product. So remember, when the value of Q is less than value of K, the net reaction will always go to the right, will always favour the production of product. So the forward reaction is favoured. However, when Q punya value is more than K, so now the product is small. So the net reaction will proceed to the left to form more reactant until the equilibrium is achieved. So now the reverse reaction is more favoured. So remember that when Q is larger than K, the reaction will always proceed to the left, will always form reactant. So the reverse reaction is more favoured. So these are the three cases for us to predict the direction of net reaction to the left or to the right by comparing the value of reaction quotient Q and the equilibrium constant K. Okay. Now let's answer a few tutorial questions before we end this tutorial class. So I am going to answer few questions. The rest of the question you need to answer it by yourself. Okay. So for this question, okay. Question is, for question 11, okay? So at 1280 degrees Celsius, the equilibrium constant Kc of Br2 gas decomposed into 2 Br gas is 1.1 times 10 to the power of negative 3. If the initial concentration of bromine gas and bromine are 0.063 molar and 0.12 molar respectively, calculate the concentration of this species at equilibrium. Okay, dia dah bagi semua maklumat. Okay, so we just put this one. So first step, we need to do the balanced chemical equation. And then we need to do the ice table. So initial change at equilibrium, now the unit is molarity because in terms of concentration. So it gives you here that the initial amount is 0.063 and 0.012. Okay, usually the initial concentration or initial partial pressure of product is 0. But since the question gives you the initial concentration of Br as well, so we need to put lah, because maybe like that is the initial maksudnya ada amount of Br tu lah sebelum reaction tu berlaku, ada amount lah. So we just assume that, okay? But usually kalau dia tak bagi apa-apa, we assume the product punya initial always is 0. Okay, so now we know that change here for reactant always negative, minus X, this one product positive, so plus 2X because this one ada 2 kat depan kan. Okay, and then so equilibrium is initial plus change, so 0.063 minus X, this one is 0.012 plus 2X. Okay, we know that Kc is equals to, the expression for Kc is equals to Br2 squared divided by concentration of Br2. Br squared divided by Br2 equals to 1.1 times 10 negative 3. So what you need to do here is you need to expand this. You need to substitute the unknown at equilibrium. So we want to focus here, right? So here we will get Kc is 1.1 times 10 negative 3 equals to BR here 0.012 plus 2x squared over 0.063 minus x. So, this one you will need to expand times dengan this one, and then this one pergi sini equals to 0, right? So, you will get here, lepas dah expand tambah semua, you will get 4x squared plus 0.049x plus 7.47 times 10 negative 5 equals to 0. And you will get x is equals to negative 1.78 times 10 negative 3. Oops. Misalah. And the positive, okay? Or x equals to negative 0.01046. Where this one, the negative value is not acceptable. Because the value of concentration and partial pressure will always be positive. So now we can say that the x that we are going to use here is 1.78 times 10 negative 3. So now we can find the value of concentration at the equilibrium. So what we are going to do is at equilibrium, the concentration of Br2 is equals to 0.063 minus x. Wait. I don't know. I think there's something wrong with the answer scheme. Can you please calculate it again for this one? How much is the answer? Because for this one, can you please find for me? I don't have calculator with me right now. So, can you help me find the answer for x? Is this sign is negative or positive actually? And this one, I suppose the answer should be 0.063 minus 1.78 times 10 negative 3. How much is the answer for this? And for the concentration of Br is supposed to 0.012 plus plus 2 times 1.78 times 10 negative 3. Okay, what is the answer for this? Okay, find the answer for me. Okay, please calculate back this question. Okay, can you help me calculate this back? What is the value of x for this and this? Okay, because I don't have calculator with me, so I use the answer scheme to find the answer. But it seems that this is rather confusing. So please help me by calculate this x for me, and then you can get this equilibrium lah. Okay. Alright, this one kan. Let me betulkan sikit. This one is 0.012 plus 21.78 times 10 negative 3 equals to what? Okay. I hope that you can help me, okay? So next, we're going to look at the second question, question number 12. Okay. If 0.024 mole of N2O4 is allowed to reach equilibrium with NO2 in a 0.372 liter flask at 25 degrees Celsius, calculate the degree of dissociation of N2O4. So this is dia dah bagi kita balance chemical equation here. So dia bagi kita Kc is equals to 4.6 times 10 negative 3. So first step, we need to do the chemical equation and do the ice table. And then second step, extract the information and put it beside the ice table. So we know that the initial concentration can be found by this one, because so this one is at initial. Okay. Alright. So it gives you the the number of mole of N2O4 is equal to 0.024 mole and the volume is 0.372 liter. Okay, so you know that concentration is equals to number of moles over volume. So we can find here the initial concentration of N2O4 is equals to number of moles of N2O4 divided by volume. So 0.024 mole over 0.372 liter, which is equals to 0.0645 molar. So here we get for ice table, the initial concentration here is 0.0 0.00645. Allah, what happened? 45 molar. I don't know what happened. Okay, and the initial for product is 0. Okay, change here is minus x. This one is plus 2x. And this one is 0.0645 minus x. This one is 2x. So we know that Kc is equals to concentration of NO2 squared divided by concentration of N2O4 equals to 4.61 times 10 negative 3. So we are going to focus here at equilibrium here, right? So we are going to focus here. Substitute this unknown into this. So we will get 4.61 times 10 to the power of negative 3 equals to 2x squared divided by 0.0645 minus x. Okay, so when you times this with this and put this here, you will get 4x squared plus 4.61 times 10 negative 3x minus 2.6 973 times 10 negative 4 equals to 0. And you will get x equals to 8.064 times 10 negative 3, or x equals to negative 9.217 times 10 negative 3, where this negative value is not acceptable. So we now know that the x that we are going to use is equals to 8.064 times 10 negative 3. Okay, so we know that. Let's have a degree of dissociation, right? Hello. So we know that degree of dissociation alpha is equals to amount of dissociated X over initial concentration C. So amount of dissociated X is equals to 8.064 times 10 negative 3. And the initial concentration is 0.0645. So you will get the degree of dissociation is 0.125. So this is your final answer. Okay. And last one. We go to question 13. It says here that at 430 degrees Celsius, the equilibrium constant Kc for the reversible reaction is 4.18 times 10 negative 3. So hydrogen gas plus iodine gas to form 2Hi gas. Question number 1. If 0.04 mole of Hi and 0.01 mole of H2 and 0.03 mole of I2 are initially placed in 2.0 liter container, in 2.0 liter container, is the system at equilibrium? Dia dah bagi you Kc. So, tapi dia bagi you initial punya, so this question asks you, so is the initial state is already in equilibrium? So what you need to do is you need to find the QC and compare it with the value of KC. So kalau QC sama dengan KC, then the system is at equilibrium. Tapi kalau QC less than or larger than KC, so the explanation will be like what I had explained to you using the table, kan? To the left or to the right. So now, what we need to do is find the concentration for all the species, and because we need to find the QC. So here, concentration of Hi is 0.04 mole divided by 2.0 liter. We will get the concentration is 0.02 molar. This one hydrogen gas 0.010 mole divided by 2.0 liter, we will get 0.005 molar. This one is 0.03 mole divided by 2.0 liter, we will get 0.015 molar. So after we get this one, we can find the QC. So QC is equals to concentration of product Hi squared divided by concentration of H2 times concentration of I2. So you will get here QC is equals to 0.02 squared divided by 0.005 times 0.15, and you will get QC is equals to 5.33. So since QC is larger than K, so system is not at equilibrium. Okay? QC is larger than KC. Sebab KC tadi berapa? 4.18 times 10 negative 3 kan? QC dia 5.33. So, sangat-sangat besar. So, QC is larger than KC. So, system is not equilibrium. So, question number 2 asks you to explain your answer in one. So, what happen bila QC is larger than KC? So, when QC is larger than KC, tadi explanation kita dalam table tadi, QC is larger than KC, right? So QC is larger than KC, so net reaction will proceed to the left to form more reactant to achieve equilibrium. So kat sini nak cakap, explanation here is the net reaction will shift to the left to form more reactant until chemical equilibrium is achieved. Tak ada chemical pun tak apa, equilibrium pun boleh je. Until equilibrium is achieved. So this is how you answer this question. Okay? So I hope that you understand this. I hope that you can have like a basic idea on how to find this and that for chapter 6.2 part 2. So I hope that, okay, one thing that I want to ask for your favor is please check question number 11 just now, the value of X, so that you can find the concentration of BR2 and BR at equilibrium. Okay? Alright, that's all for today. I hope that you will understand my video for today. Kalau tak faham apa-apa, you can ask me. Okay? So that's all for today. I hope that you guys have a good and nice day ahead. So yeah. Bye. Assalamualaikum.